Okay, so here's the proof of Lemma 3. Okay, so we're going to do the first sentence and then we'll do the second sentence. So the first sentence is covered by this, and I'll go through this. It says, the matrix H is invertible if and only if it is non-singular, and thus Gauss-Jordan reduces to the identity. We know that from previous discussions and theorems, okay, lemmas and whatnot, okay? Now, by corollary 1 from the last section, we can do this reduction with elementary matrices, R sub R, all the way through R sub 1. So remember, we can compose this product of matrices in this way such that we're going to get the identity. So that's from corollary 1. Okay. Now remember this. We're going to refer back to this. Now it says for the first sentence of the lemma, note that elementary matrices are invertible because elementary row operations are reversible. Okay, so that should be plain. Okay, and that their inverses are also elementary. So the inverses of these R's exist, right? And they're also elementary. Okay, so that's also important. Okay, now given that, so now what we can do is we can apply the inverses of these R matrices, these elementary row matrices, or reduction matrices, from the left. So what we can do is we can start applying, for example, the inverse R1, right? R sub 1, this inverse, right? Here, we can start multiplying on the left of each side, right? Or not this one, I'm sorry. Looking at the wrong one. This one. Start with this one. So this is apply this inverse from the left of both sides. So what we're going to do is we're going to multiply by R inverse of sub R on both sides, right? So we're going to get R sub R inverse, right? Or excuse me, R inverse sub R. So here. Now what's going to happen here? If we multiply this side by its inverse, this is just going to give us the identity, right? And then we'll have R inverse. And then we're going to do the same thing with this inverse here, which will be the next one. And so, etc. So what we're going to do is we're going to start multiplying both sides by each subsequent inverse of the elementary reduction matrices. Okay, so these elementary matrices. So what's going to happen? Well, if we keep doing that, the result gives us H as the product of the elementary matrices. Because what's going to happen is we're going to have, over here, we're going to have R inverse. We're going to start multiplying I, because again, we're multiplying both sides of the equation by the subsequent inverses. And so what we're going to do is all these matrices are going to start to become I, and so it's just the identity matrix, which is basically like 1, right? So, you know, like in real numbers, 1 times any number is just itself. So what we're going to end up doing is over on this side, all of these elementary matrices are going to end up becoming I, and then I times H is just H. But over here, we're going to just end up having I times the product of all these inverses, inverses. And so what we're going to find is that H becomes exactly what the result says. It's going to become a product of just all of the elementary matrices. Boom, we're done with that one. Okay. Now, as far as the second sentence, we just have to recognize that if we group, just think about this. If we group these elementary row operations, this times this equals I. Well, we just have to recognize that this product of R matrices has to be the inverse of H, because remember, the only way we can take a matrix times another matrix to get I is if this matrix is the inverse of h. So that's it. Once we recognize that, then we're done, and the result is proven. Have a great day.